Neuromorphic vision systems are designed to process visual information efficiently, but they face a strict, fundamental energy-to-information trade-off. In an event-based spiking neural network, an architecture transmitting data using discrete electrical impulses rather than continuous values, highly predictable incoming events consume valuable compute cycles while providing zero new information to the system. The actual task-relevant signal is carried almost entirely by surprising or irregular events. When the visual input suddenly changes, the resulting spikes contain the specific data the network needs to make accurate classifications. To build an efficient model, we must filter predictable noise before reaching the processing layers, without severing the signal path. Solving this redundancy bottleneck is a primary hurdle for scaling SNNs. To find a solution, we have to test different filtering mechanisms against standard industry benchmarks. We can evaluate this trade-off using NMINIST. It's a standard neuromorphic dataset of handwritten digits captured by event-based vision sensors, making it an ideal benchmark for spike filtering. Baseline plots, top right. A vanilla SNN processing 3.52 million events at 75.05% accuracy. The modulated front-end filter plots, top left. Discarding 1.66 million events, it retains just 53% of input data, yet achieves a higher accuracy of 75.75%. How does discarding nearly half of a dataset's event stream improve a neural network's accuracy? When engineers want to suppress redundant spikes, the conventional approach relies on explicit inhibitory wiring. The prime example of this topological approach is predictive coding light, or PCL. PCL attempts to suppress predictable spikes by building explicit physical pathways. It relies on learning specific inhibitory synapses that route backward from the output layer to the input layer. To calculate which incoming spikes to suppress, PCL uses inhibitory STDP. STDP, or spike timing dependent plasticity, is a biological learning rule that adjusts the strength of connections based on the precise timing of spikes. The network constantly updates these weights, attempting to learn every single suppression route to cancel out redundant signals. This design introduces a specific structural complication. It tries to solve an energy and redundancy problem by adding wiring overhead and highly complex local learning rules. Let's look back at the scatter plot to see how PCL performs on the NMNIST benchmark. PCL does successfully drop data. It retains only 51% of the input stream, putting it on par with the modulated model's data reduction. But there is a performance cost to this topological approach. Classification accuracy drops to 71.25%. The explicit structural constraints required by PCL appear to have degraded the true signal path while trying to eliminate the noise. This comparison indicates that for this task, pruning events through explicitly learned structural topology creates a performance penalty that a front-end filter avoids. Instead, we can move away from explicit synaptic wiring by looking at a different biological inspiration, chemical neuromodulation. We are not attempting to model detailed neurotransmitter chemistry. Instead, we are abstracting the core concept of modulation. We can define this neuromodulation as a slow, local internal state that loosely envelops the flow of information, rather than acting as a rigid physical gate. By treating filtering as a generic internal chemical state, the system bypasses the structural complexity and wiring overhead of PCL entirely. Physically, this solution is positioned as a single, self-contained filter block. It sits strictly before the first SNN layer, directly intercepting the data stream before it reaches the standard downstream surrogate gradient LIF units. LIF units, or leaky integrate and fire neurons, are artificial neurons that accumulate electrical charge over time and fire a spike only when a specific threshold is met. This block acts independently of the main PyTorch training loop. It serves purely as a dynamic data throttler. Inside the filter block is the first internal component, the short-term predictability trace, representing the immediate history of incoming data spikes. The second component is the slow internal modulatory state. This isolated, gradual threshold shifts independently beneath the fast-moving trace. The interaction between these two elements creates a keep-drop gate. If an incoming event highly correlates with the dense predictability trace, the gate recognizes it as redundant. The gate closes, and those specific data points are dropped. However, if an event is irregular or surprising relative to the trace, It triggers the keep condition. The gate opens, and those distinct, surprising nodes pass through to the downstream LIF units. This generic gating rule operates without needing to learn any explicit inhibitory synapses. The front-end filter acts like a chemical bouncer, turning away predictable noise, so the main neural network only has to process the most informative surprises. This brings us back to the empirical anomaly. How did stripping away 1.66 million events result in a 75.75% accuracy? To understand the accuracy bump, we have to look past the input layer and measure the internal activity of the network itself. We use hidden layer spike counts to measure internal signal richness, mapping that count to the diameter of each node. The vanilla model establishes our internal baseline. After processing all 3.52 million input events, it generated 1,758 hidden spikes. We can observe the failure state of PCL here. Despite its heavy wiring, its internal representation dropped to only 1,648 hidden spikes. In contrast, the modulated model generated 1,779 hidden spikes. This is a subtle but critical shift, surpassing both vanilla and PCL in internal activity. This is a pure signal-to-noise ratio effect. By generically throttling redundant spikes at the front door, the downstream LIF units were starved of noise, but fed a concentrated diet of signal. Less input data generated a richer, more active internal representation within the network. That concentrated signal directly drove the superior classification accuracy. When optimizing event-based pipelines, explicit wiring architectures can create unexpected bottlenecks. Adding structural constraints to solve data redundancy may degrade the very system it is meant to optimize. The generic modulatory mechanism proves that we can achieve higher accuracy with lower data volumes without adding a single extra wire. This pointing to a broader principle in machine learning engineering. Abstraction often provides a more scalable path than explicit simulation. In the pursuit of energy-efficient neuromorphic vision, abstracting modulation into a generic state provides a flexible, high-performing alternative to the overhead of explicit wiring.